All right, so let's do a quick recap of the topics we've covered so far. I'm just going to scroll back through the notes. If you guys don't have them in front of you, don't worry. I'm just going to talk about some of the main highlights. So I've got 55 slides to get back through. Okay, so our first topic, we talked about introduction to electrostatics. And we basically did a little mini history lesson on a few different historical figures who discovered things about electricity. Thales of Miletus. Anyone remember, without looking in your notes, what he discovered? Yeah, basically, he noticed that, no different than maybe you end up discovering that, a hair is stuck to your shirt. And you're like, well, why is it sticking there? It seems to be opposing gravity. Well, he discovered that stuff seems to stick to each other if it was electrostatically charged. At the time, they used something called amber. We use different things now, but he discovered the basic starts of static electricity. I forget what Gilbert was about, so if I forget, obviously it wasn't that important. Ben Franklin. Go back and look through your notes later. Ben Franklin, the thing I remember most about this one here is that he actually had his son do his electricity experiments, and he didn't do it himself. But he basically was the one who we credit with the term electricity, the whole kite kind of experiment, trying to figure out whether electricity could run through the kite. At the time, one of the problems that they had there is that they didn't really fully get the concept of what electricity was. They thought that positive charges moved. Have we talked about this already? The concept of positive charges versus negative. They didn't know that electrons existed, and so they thought that positives flowed through things. They thought there was this juice, maybe, this electron flow. They just didn't know it was electrons that flowed through stuff, and some stuff had more of it, and other stuff had less of it. And they really didn't figure that stuff out until we learned more about the model of the atom currently. So under modern theories, we talked about how Ernest Rutherford discovered in 1890 something. They discovered the nucleus and discovered that electrons are actually orbiting a nucleus. You guys recall this concept? And so it's really electrons that seem to be moving. And so if you have extra electrons, it means you're negatively charged. In order to become positively charged, you don't have more protons, though. You've just lost your electrons. Does that make sense? There's a huge overlap between this and chemistry. Today, especially for you guys over there, where you've done Chem 30, I've got a thing I can relate to a Chem 30 topic, and then for you guys, we'll just show you an extra, I guess. But you guys should know the word anion and cation. You guys remember those words? Cats have paws, so cations are positive. So anyways, just the overlapping idea of positive charge is really the lack of electrons. Negative charge is really excess electrons. So that's where we started with just some basic history. We talked about different things that either have the ability to conduct or insulate, where they either want to lose their electrons or they don't. In chemistry, we have a term for this. It's called electronegativity. You guys recall this from last year? Electronegativity. It's basically the tendency to want an electron. Fluorine really wants electrons, whereas sodium really doesn't want electrons. And so if you want electrons, you're an insulator. You hold on to them. Whereas if you don't want your electrons, you can conduct because you can let the electrons flow through. So, I have some charts here just showing you things that can conduct and don't conduct. Then we talked about two really important words, definitions. Let's see if I can find them highlighted here. How do I not have it here? Oh, here we go. Conduction and induction. Okay. Conduction is where you take something that's charged and you literally touch the charge off to something else and it shares its charge. It shares it based on surface area. So if I had something that was very large object and I touched something very small, only a small portion of the charge would go from the large object to the small object. Right? But if they were, say, evenly sized, well, then they'd pretty much split the charge in half. So if this were a charged object and this were a non-charged object, and I touched them together, they'd each take half of the charge, more or less, if that makes sense. So that's induction, where you literally touch one object to the other one. Sorry, that's wrong. Conduction is where you actually touch this object and this object together. Induction is where you bring the object really close, but you don't touch. And it causes a separation of charge where if this is negatively charged, well, all the electrons will try to go as far away as they can. They try to leave as far as possible. and it creates like a dipole where this becomes positive and that becomes negative. You guys recall this concept? There's even a question on your assignment about how lightning works that way. Essentially what happens for lightning is that clouds build up a huge static of electrons, somehow through whatever process. In the bottom of the cloud accumulates electrons. So many electrons that the Earth itself actually will undergo induction. Right? And what ends up happening is the Earth, you and me and the ground and whatever, right? We all have electrons. But what ends up happening is those electrons get pushed away from the surface of the Earth due to the fact there's so many electrons in the clouds above you. Right? And so all those electrons get pushed deep into the ground, creating kind of a dipole where you can imagine here's the Earth, here's the cloud above. The cloud above is negatively charged. The Earth then becomes a positively charged surface. And eventually it becomes so dramatic that eventually, rather than it just being induction, you'll actually see the sparks will actually jump from one object to the next. And I'll even be able to show you that on the Van de Graaff generator on Thursday, the idea of being able to watch the spark basically jump from here to here as the electrons finally can't take it anymore, and they move from the negative section to the positive section. And that big spark, that discharge, is what we know as a lightning bolt. Right? Essentially, it's a form of electricity. It's a movement of electrons. Okay, what else should I talk about? Well, it's kind of the basics here. I showed you guys the electroscope. We'll actually play with those on Thursday. But if you bring the positively charged object near, it causes this to become negatively charged, and this positively charged. And then these two little leaves right here, they open up because these two positive things will repel each other. You guys recall this? Okay, just kind of doing a quick review. Let's move on. The next day we talked about Coulomb's law. And this was where we tried to put some sort of mathematical equation to what we were able to witness. One of the things I mentioned is that this part of physics here where we're working with, it's very different than kinematics and dynamics and momentum, because all of those are very tangible things where I can throw a ball, I can crash cars into each other, and it's very visible. I can see that happening. I can really intuitively understand what's happening. But this sort of stuff here about electrostatics and magnetics, we can't really see the force that's occurring, but we can see the effects of the force. Remember me talking about similar to like the wind? I can't actually see wind. Wind is really just moving particles hitting me, right? And if they're moving with a lot of energy, then you say it's really windy out today. But I can see the effects of the wind. I can see a flag ruffling in the wind, or I can feel it hitting my body, but I can't really see wind. You know what I'm saying? It's very similar with magnetics. There's a force between magnets, and there's a force between charged particles that I'll never be able to see, but it's still there. Something's obviously occurring, and I can see the effects of what's happening. And so the point I was trying to make here is that once physicists understood what was happening, they had to try to find a way to quantify this. They knew that you could make stuff stick together, magically, right? Like literally magicians would use these principles for some of their tricks. The question was, how can we figure out how to quantify it? Because otherwise it's not physics unless you can put some numbers to it. So there was this experiment with kind of the wire that could torque. It was like the Cavendish experiment, only this guy did it first. This is Coulomb's experiment. Same kind of concept. You have these charges. They should either attract or repel. The wire rotates, and it allows them to calculate this number right here, the electrostatic constant. It's way larger. One of the reasons why is that proportionally, although gravity is a very large force, between, like, say, me and Darian, there's no gravitational force whatsoever, right? I'm quite small, relatively speaking. So is he. The distance between us is pretty far. There's not a lot of gravitational force. But if we were charged objects, we might even have it happen where you've seen this before, right? Where like your hair ends up getting electrostatically caught on a shirt, right? I mean, things of our size, we can see the electrostatic force between them, but not the gravitational force. So that's why this constant is so much larger. But honestly, it's the same formula, right? A constant, then two objects that have a mass or a charge divided by the distance between them. Straightforward? So we learned about that formula. We talked a little bit about a coulomb. A coulomb is basically a fancy way of saying, let's not count electrons one at a time because that's dumb. Rather than say, hey, this guy has one extra electron, that'd be ridiculous. So kind of like we have a mole in chemistry to describe a lot of atoms, or for like eggs or for donuts, we measure them in dozens. We do the same thing with coulombs. Okay. A coulomb is basically a lot of electrons. Okay. It was written here. Here's the official number. It's this many electrons. This is what you'll see on your formula sheet. 1 electron is a very, very small percentage of a coulomb, a 10 to the minus 19 of a coulomb. So it's just our way of measuring how much charge something has. Do we care about the positives or negatives? Not when we use the formula. Okay, so don't worry about putting in pluses or minuses. Just worry about figuring out whether they attract or repel later, which is why many of the formulas you see have the absolute value signs around them. I don't know that this one here does, but we usually use the absolute value signs around them to indicate that we don't actually care about direction. We did a bunch of examples. One of the things you guys probably will come to hate, and probably already do, is the two-dimensional problems. Remember doing some of these? Break it up into x, break it up into y, find the new x, find the new y, hypotenuse them to find a new distance or whatever it is, and then inverse tan to find an angle. As you're called doing questions like this. You get one on the diploma. It'll take you 5 to 8 minutes. If you're fast, closer to 5. You'll hate it because it sucks, because it just takes a long time, that's all. Okay, and then the last topic we talked about before our break, it was on fields. Fields are really described as like a way to understand this action at a distance. Right? I can understand the force of me throwing this pen if I literally threw it. Right? That's very intuitive. It's an applied force. If I pull it back, I understand that force there, right? But why did that happen? I didn't throw it down. Right? Well, it's due to a gravitational field. And that's our way of trying to describe these actions that happen without us physically being able to see the push or the pull. There was a pull between the Earth and the pen, causing those two objects to come towards each other. Right? So a field is the way we describe these actions at a distance, which is what I have highlighted down there. Do you remember how we define a field in electrostatics? Which way do we draw the arrows? As if it's an imaginary positive charge, yeah. We just had to pick one, positives. I'm guessing the reason why they went with a positive is that 200 years ago they thought that positives moved because they didn't know about electrons yet. So, but honestly, it doesn't really matter, right? You just pick one or the other. So a field is defined as what a positive would do. So you can see right here, a positive would want to be sucked into a negative. Right here, a positive one would want to get pushed away from another positive. So, today we're going to talk about this type of field, by the way, where you have 2 plates. We'll get to that in a second. Here's some formulas we would have worked with, and I hope you guys would agree with me. The formulas themselves are not that hard. Like, they're mostly 2, 3, 4 variables at most kind of formulas. The biggest thing you got to make sure you're clear on 2 things. One, you got to figure out how the direction is going to work, whether you have to deal with positives and negatives, but you kind of just do that at the end. The other one is you got to be super careful about what F and E stand for. F is a force, it's a vector. E, without a line on top, is energy, which is scalar, something different. E with a line on top of it is an electric field strength, which is a vector, so direction does matter again. So you just got to make sure you know what your letters are and don't get them backwards. So here's our first formula. If you take your amount of electric force and divide by charge, it gives you the field strength. Kind of similar to how we did that with gravity as well. Then we learned a formula later about this one right here. If you want to find the field strength of a individual point charge, it's kq over r squared. So this is the field of just one particular dot, how much field strength it has. And that's kind of where we ended, only we got back to that same dumb example where you might have to do this in 2 dimensions as well. So, okay, that was kind of the Cliff Notes versions. That's what you missed on Physics 30. Is that good? Okay, so let's start with something new then. Our last kind of topic in the section is about something called electric potential. So This has huge overlaps with chemistry, so I'm going to try to relate those and weave them in wherever I can find an example. I want to talk about two plates. Imagine you had one plate right here and one plate right here, and one of them was positive and one was negative. Okay. Right off the bat, for you guys in Chem 30 who took Chem 30, if I had two plates like that, what is this? It's a battery. Yeah, who said that? Good job. Yeah, this is essentially a battery, right? Where you have a positive side and you have a negative side. If you wanted to throw that in there, we could actually label them using their official terms in chemistry. You guys remember what they're called? Similar to the charges. Good, anode and cathode. Fantastic. And do you guys remember which ones are which? Negative things are anodes, and positive things are cathodes. And so essentially what we're going to talk about here is a crude sort of battery, where you have two different charged sort of, in this case they're going to be plates. But you know how in chemistry we would have used like electrodes, we just used like pieces of metal going into, I don't know, what were they, beakers? Right? Same sort of concept here. What we're having happen here is the electrons are going to flow from, let's see, which way do they go? They want to flow from the anode to the cathode. Wouldn't that make sense? If you were to put an electron right here, there's an electron sitting here, what would the electron want to do if it was near a negatively charged object? It wouldn't want to be near a negatively charged object, right? It would want to be repelled, and so the electron would go towards the positive. We have a similar example for this. I'm going to relate this to gravity. Imagine that these things right here weren't plates. They weren't electrically charged plates. Imagine they were just gone and it was gravity. What would gravity cause things to do? Well, wouldn't it cause something to basically fall downward? And so in terms of gravity, we would say that it has potential energy. Does that make sense? Right? Well, we use that same word here. I've actually got this written in this little section right here. A charge in this field would move from an area of high potential to low potential. So let's pause for a second and look at this diagram. Let's consider an electron. Where would the electron have high potential? Good, close to the negative plate, right? If this was an electron, and again, we have to depend on which charge it is, but if this was an electron right here, up here, this would have high potential. I mean, wouldn't this be really similar to just the random object that I dropped, right? The higher above the ground it was, the more potential energy it has. Right? Well, what would that potential energy do? Would it just stay as potential? It would. No, turn it to kinetic, right? Don't be afraid that Mr. Pi is at the back of the classroom. Right? It would change from high potential to low potential. In the meantime, the electron would then change, right? That potential would change into kinetic. Right? And that electron would move from one side to the other. Isn't that really how a battery operates? Right? Electrons basically flow from one pole to the other pole. They run, usually we run them through a wire, but those same concepts still apply. So what we're going to use today is use the word electric potential. That's kind of the key word here. We're talking about what sort of potential energy does an electron or a proton have. Okay. Now, I mean, if we talk about a proton, just flip the scenario, right? So where would a proton have high potential? Close to the bottom plate, right? Close to the cathode, right? Here's where a proton would have a higher potential energy, right? And it would have a tendency to travel that way. Sound good? Now, before we go any further, though, we should talk about how a field works. I pulled this diagram out of like a textbook here, and it has field lines being shown here, but it didn't draw any arrows. If this were field lines, which way would the arrows point then? Down or up? Good, up, yeah. The reason why is that field lines, like we just said earlier, are based on what a proton would do. So these guys would want to go up. Does that make sense? Okay. Okay, so that's what I have to talk about in this next slide here. I don't want to read word for word what's on there, because you guys can do that, but really think of this similar to gravitational potential energy. There is a potential due to something just falling due to gravity. If you've got charged plates or charged objects, same thing happens, right? Anything charged will want to be repelled from one side and attracted to the other side. So we have a whole bunch of different vocabulary I need you to know, all these words. The first one is like electric potential, which is what I gave the title of our notes to, but there's other ones known as electric potential difference, but the most common one we're going to use here is known as a voltage. And I'm sure you've heard that word before. So what we were just describing is how many volts something has. Okay. How much potential it has. You guys ever heard of like a 5 volts versus 1500 volts? You've heard that term before, right? Well, the more voltage it has, the more potential it has. So now it's not necessarily based on distance, but think of it similar to gravity. Okay? If you were to use a 1.5 volt battery, it's like that. It fell just a small amount of difference. How much potential did it have? Well, it didn't have a whole lot of potential. Right? Whereas if you use a 9 volt battery, that was a 9 volt battery. Does that make sense? Right? The idea that has like a similarity to gravity, the more voltage you have, the more potential there is. Now that doesn't mean that the plates are further apart. Okay? That's the first thing that kids think of is I think we'll just put the plates really, really far apart. That gives it more potential, but that's not really what it's based on. It's really based on the strength of those plates that you have for your anode and cathode. So they could be close, they could be far. That's not really what we're saying. Here's what ends up happening then. If you were to have a couple of plates right here, and you were to like say shoot an electron through, there's actually a lot of famous experiments based on this. And if you guys had ever heard actually, like those like super old television sets, this is actually how they used to make pictures. They used to use something called a cathode ray tube, where essentially you're going to shoot a charged particle into a field, and then rather than the particle staying on a straight line trajectory, can you guys intuitively make sense of this diagram here? Right? Lost our picture here. Right? The electron, as soon as it enters the field, as soon as it enters the region of influence where there's going to be a field, the electron would now want to be attracted to the positive plate. And you can actually deflect particles off to the side one way or another. And that's how they actually used to make old school televisions work, is they used to shoot particles towards like a phosphorescent screen. And depending on how some magnets and electronics work, they deflect them upwards or downwards, side to side, and that would cause the picture on like your old like Fox TV screens. Right. These guys right here, they obviously operate different. Okay, let's talk about some of the units and formulas we want to talk about then. So in this scenario here, another way of approaching it is to think of voltage as how much change you have per charge. Okay? It's your change in energy per charge. Let's pause for a second here. You know how, just like with my pen falling to the ground, we could change its potential energy to kinetic energy? Well, if you think of this from an energy perspective then, I mean, that kind of makes intuitive sense, that your voltage is how much energy change could occur, but aren't you going to have more energy change take place if you had a like 1 Coulomb object? Wouldn't it be more in a 5 Coulomb object or a 100 Coulomb object? So wouldn't it be fair to consider the object being moved? Like, let me go back to a picture here. Here I have an electron, right? An electron has, a very small amount of charge, right? Well, it wouldn't be fair to compare something that has 1 Coulomb to something that has 100 coulombs, because isn't one of them going to have a different energy difference? Isn't this one going to be sucked across, at a medium speed, and isn't this one going to be pulled across really fast? Just based on the fact that one of them has more charge to it. So if you want to figure out your voltage is based on how much energy change you have, but it's per how much charge you're looking at. Does that make sense? So here's our next formula here. The amount of voltage you have is how much energy change can occur. Now remember, this is an E without the little line on top. So if it had the line on top, it would be field strength. Since it doesn't have the line on top, it's now energy. Yeah. So your voltage is how much energy change you have, but you have to divide by how much charge the object that moved was, right? Because if it's got 1 Coulomb or 10 coulombs, it makes a difference, right? So here's another thing we need to point out. Big exclamation marks here. Voltage is scalar. Why? Why would voltage be scalar? Well, what's voltage based on? Well, what's energy? And it's also based on charge. Charge, I guess you could say it kind of has a direction, but it doesn't really have a north, south, east, west direction. It more just has a positive, negative direction. So really, charge is also kind of scalar in a way, right? because it doesn't have a north. You could say it's 5 coulombs north, right? So voltage is scalar. We don't care about the direction. Okay. And then my other reminder here, it's not field strength here. That's the biggest problem I find kids have is they try to use these formulas in that section on their formula sheet here, and they get the E's mixed up because they are different. So, one more thought here. Voltage is actually measured in joules per coulomb because it's how much energy you get for how much charge you have. But we often change it to the capital V for voltage. Right? Volts is based on Alessandro Volta. You guys ever heard his name before? The Russian battery maker, essentially. Before I go too far, I want to try to overlap this with chemistry a little bit here, just because I know a few of you have done chem, and next year more of you will do chem. You guys remember talking about voltage in chemistry 30? So, for you guys in grade 11, we're going to talk about this table next year, obviously. But for you guys in grade 12, do you recall this table here? Essentially, you have flashbacks. So essentially the way this table worked, if you guys recall, is this table allowed you to find a voltage. And at the time, I just skipped over this word, but now maybe it makes sense in hindsight. That's known as how much electric potential something has. Right? Electrons have the potential to go from one side of the battery to the other side of the battery. The question is how much energy will they be able to pick up during the course of them doing that? Does that make sense? So that's their voltage. And then the way we figured this out, if you guys remember from last year, is we found these couple of numbers here. And we just subtracted them from each other. Right? So it's actually a really easy table to work with, but there is a huge overlap to chemistry. So, anyways, back here. So here's a picture of a battery just to kind of help this illustration kind of fit forward here. If you have a battery, electrons are going to go from the negative pole, the anode pole, to the cathode pole. Right? They're going to go around some sort of circuit. Now, the length of the circuit does not impact the voltage. So again, the length of the circuit does not impact the voltage. Okay? In gravity, the formula for gravity is mass times gravity times height. So in gravitational potential energy, the distance you travel is actually something that we need to consider. Okay. But if you were just to have a longer wire, that doesn't actually increase or decrease your voltage. Because your voltage is based on how much energy you have per unit of charge. Okay. So it's not based on distance whatsoever, at least in this sort of scenario here. Okay. The other word I want to point out is how kids often get voltage and current backwards. You guys ever heard that term current as well? Voltage and current. They're similar. They're not synonyms. They're not like, they don't mean the same thing though. Current is basically how much charge is able to flow per second. So current is actually a measure of like how much is possible, but voltage is a measure of how much energy they're going to be able to obtain. Do I have my water tower analogy here? I do. Okay. Let's talk about my water tower analogy, because I like this one here. Imagine you have a water tower filled with water 20 feet above the ground or whatever. Okay? And let's say you put a hole in the water tower. Well, the water at the top of the water tower would be able to flow out of the tower, right? Well, its voltage then would be how much energy you'd be able to have between the water at the top and when the water hits the ground. Except that's an analogy for voltage. How much energy the water is going to have when it hits the ground. Now, if your water tower is this far above the ground, well, it's not going to have that much voltage, right? It's not going to give you that much energy. Whereas if the water tower was way up in the sky, well, then there would be more voltage, there would be more potential energy to it. Does that make sense? Now, here's where current comes in. Current is how much is able to flow. If I were to put a hole this big inside the water tower, it's just going to drip out little by little by little. But isn't the water still going to gain the same amount of energy? Because as the water falls from top to bottom, it's going to gain however much energy the height happens to be. Does that make sense? However, your current is based on the hole. If you had a small little hole, it flows out at a pretty slow rate. But if you had a big, massive geyser hole, right, can you see how the battery is going to discharge faster? And all of the water is going to go gushing out? That's your current. Okay. Now, your current is really related to something called the resistance, which I don't have on this slide, but I know it's on a future slide. Okay. Resistance basically is certain types of materials allow electrons to flow through nicely. So like for example, copper doesn't have a lot of resistance, therefore we're allowed to, we use copper as our wiring because the electrons can flow through it without them getting slowed down, if that makes sense. But there are certain types of materials where the electrons can pass through, but they have a harder time, if that makes sense. So if you can imagine the analogy of the water tower, like a big gapping hole is like copper wire where the electrons, they flow no problem, right? Whereas a small little hole, the electrons are able to kind of run through that wire, but it's like they're like wading through like a swimming pool. Like it just takes them a long time to get from one place to the other. Does that make sense? So to recap, voltage is how much energy you're going to have by the time you're done. When you start here and end here, your change in energy divided by your charge, that's your voltage. Your current is basically how fast that occurs. The faster the current, the more charge it's going to go zipping by. Here's a slide that I have that, here's where it talks about resistance. Depends on how much current is resisted. It could be by the wire, it could be by, like, say, the light bulb that you use to, you know how you're going to use the electricity for something? It's going to have to go through something that, you know, does something. That could be your resistance. So, let's move on. Let's do some examples now. That I've given you the formula, let's do the math. And I think you guys are going to find this to be one of the easier things to do. Because like the formulas are pretty straightforward. You just have to know which one to use. So I've got an object. I'm going to tell you how much energy it's going to gain as it goes through the field. Find the voltage. So here's the formula I just gave you. Your change in voltage, not a vector, is equal to your change in energy, still not a vector, divided by its charge. So it gains 2.6 times 10 to the 3 joules. And that happened to a 3.4 Coulomb object. Just divide the two numbers. It's as hard as it gets. Uh, 7 is 64. So with sig digs, let's call it 7.6. Let's call it 7.6 times 10 to the 2. And then your two possible units are either a joule per coulomb, or you could call it a volt. That's what voltage it has. Can you guys see why it makes a difference based on the charge, though? If an object gains this much energy, but, you know, if this was a 3.4 Coulomb object, what if it was like a 0.01 Coulomb object and it gained that much energy? Well, this number right here, if you change that number, that would change the voltage considerably, right? Like if this number was a, like let's say this was a 300 Coulomb object and you were dividing by 300. What would it do to the voltage? Well, it would make the voltage drop, right? Which makes sense because it wasn't really the plates of the anode and cathode moving the object then. It was just the fact that the object itself was so highly charged. So, is that straightforward so far? Okay. Now, the next thing I need to point out is that we're often not going to work with standard units of joules for energy. There's actually a second unit of energy that we need to start working with, known as an electron volt. Okay? It's known as an E capital V. Small e for electron, capital V for volt, and this is another unit of energy. And basically, it's how much energy it takes to have one electron undergo movement through a field that is powered by something that is 1 volt. So if you had a 1 volt battery, it's how much energy it could give to an electron. Say that again here. An electron volt is how much energy a 1 volt battery could give to a single electron. And it's a much smaller unit of measurement because often joules is just too much. We don't get that many joules. So here's the number you need to know. This is on your formula sheet. So on one of those like tables somewhere. This is how many joules is in an electron volt. 1.6 times 10 to the minus 19. That's how many joules is in an electron volt. How many volts or how many joules it takes to move one electron using 1 volt. potential energy, basically. So it doesn't change the math. It doesn't become that much harder. It's just you have to change your units. So let's try this example here. We're going to figure out how many electron volts are needed to move an alpha particle through this voltage from the negative to the positive plate. Before I even get into the math, I just want to draw a little bit of a picture here. Imagine we have a couple of plates to a battery. So one of them is the negative plate. One of them is the positive plate. And we're going to take an alpha particle. Do you guys know what an alpha particle is? I told a few of you before. Do you know what it is? It's a helium nucleus. An alpha particle is a helium nucleus. It basically has 2 protons and 2 neutrons in it. Sometimes you'll see it notated with this symbol right here, 4, 2. You guys remember in chemistry what the 4 and 2 stand for? What's the 2 at the bottom of this sort of notation stand for? 2 protons. It's its atomic number. Let me do a different one here. If I give you hydrogen 1, 1, it means that hydrogen has 1 proton, and then it has a total mass of 1, which means this one has 0 neutrons. If I give you 12, 6 carbon, this means you have 6 protons because it's carbon. And then how many neutrons would you have? Because it adds to 12, right? 6 plus 6 is 12. If I gave you 13 and 6, 7 neutrons. You guys recall this? Okay. So an alpha particle is basically a helium nucleus. It has 2 protons and 2 neutrons for a total mass of 4. And it's often given this charge of 2e. But it's positive 2e. Basically, it's got positive, because it's got 2 protons, right? 2 elementary charges there. So, okay, if I can put it in my picture here, we're going to move the alpha particle from the negative to the positive plate. So I'm going to put the alpha particle right here at the negative plate. Does it intuitively want to move from there? No, because its charge is positive, right? 2 positive charges. It doesn't want to move, so we're going to have to do some work to cause it to move. You know what I'm saying here? We're going to have to physically use some work. Don't forget, work is essentially energy. We're going to do some work to get it to go from the one plate to the other plate. Does that make sense? The question we're being asked then is, how many electron volts would we need to do that? Now, we're not talking about joules. We're talking about a very, very small amount of energy for this to occur. So we just have to do the unit conversions. So use the formula as it was. So that was, what was it? Your voltage is equal to your change in energy over your charge. The only difference now here is that your voltage is 6.7 times 10 to the 2. Let's call it joules per coulomb. We're looking for our change in energy, and we just have to divide by our charge. What's its charge going to be? 2 like elementary charges. Since an elementary charge is 1.6 times 10 to the minus 19, this bottom number down here is going to be 2 times 1.6 times 10 to the minus 19. Let me see if I can follow that again. You know how we measure coulombs is just a whole lot of electrons? Okay, 1 electron or 1 proton would have the charge of 1.6 times 10 to the minus 19. That was if there's 1 charge to it. But an alpha particle is a particle that has 2 protons in it, so it's going to be 2 times that value. Come on. 2 times that value. That makes sense? So when you multiply this up over here, oh, hang on, that's the right unit though. That is not a joule here, that's a coulomb. 1 electron has a charge of 1.6 10 to the minus 19 coulombs. You have 2 of them. You have that number right? Yeah. So your change in energy is going to be equal to 7.6 times 10 to the 2 multiplied by 2 times by 1.6 times 10 to the minus 19, there would be this much energy, 2.432 times 10 to the minus 16 joules. Was able to get that value? So here's the problem. That's a ridiculously small amount of energy required, right? Like 10 to the minus 16 joules of energy is so small that we're going to use a different unit. But rather than like use, those prefixes where you can use things like atto, femto, pico, nano, rather than use those, we just made a whole new type of unit entirely. So the last thing you would do is you would take this number here, 4.32 times 10 to the minus 16 joules, and you're going to convert it using the conversion ratio, which is that in 1 electron volt, where is it here? There is 1.6 times 10 to the minus 19 joules. I used the, no, I could use the right number there. One thing you guys will notice is you're using this number a lot, because this number right here is the amount of charge in an electron, but it's also the conversion ratio from electron volts to joules. So essentially you have to redivide this number by your 1.6 times 10 to the minus 19 number. So I got 1520. All right. So 1.5 times 10 to the 3 electron volts. That would be how much energy it would take. Another way of writing it, 1.5 kilo electron volts. Sometimes we'll talk about things in kilo or mega electron volts. So when you're kind of caught in that gray area where the amount of joules is way too small, we can then convert it to electron volts, but sometimes you may want to then convert your electron volts to a kilo or a mega electron volt. We'll follow that. It's not, we don't change the math, it's a new unit type, that's all. So the thing I need you guys to be aware of is that if you guys have your formula sheet in front of you here, like the constants, the fifth one down, you guys see the fifth one down is elementary charge. One electron and proton is 1.6 times 10 to the minus 19 coulombs. It just so happens that the way we chose our units, we decided to call an electron volt that many joules as well. You guys see how that 1.6 times 10 to the minus 19 is on there twice? So you may end up using the number in the first formula and then using that same number again when you convert it later. So. All right, that makes sense? Okay. You might ask the question, why are we using plates? Like, I know we just kind of started and hopped into using plates. Why would you use plates? I actually have the reason here. It's to ensure that the field is going to be uniform. If you use plates where you've got these like nice flat anodes and cathodes, these I don't know, use a disc or use a bar of some type, what it's going to do is it's going to cause everywhere in here to have a uniform field. Okay? Because what would happen if you were to use like a curved object and another curved object? Let's say that this was positive, and let's say that this was negative. Well, sure, you would still have a field where it would want to go this direction here, but if they were like curved surfaces, you may end up having like slight differences in terms of like it not following like a straight line path. You know what I'm saying here? So the nice thing about using solid flat plates here is that it's going to ensure that the field is uniform, and it also means the voltage is uniform. That's the way that you ensure that you have a constant amount of voltage. Okay. So what I've got here then is a proof for another formula we have. This formula basically, let me walk through the process here. We know that voltage is change in energy over charge, right? That's just the formula we just gave you. But isn't energy the same as work? And isn't work force times distance? So because you're going to have an object, like say a positive item right here, and it's going to move from here to here, it's going to undergo some work, right? It's going to change its energy. So work is force times distance. Force times distance is energy. You see how what I've done right here is I've taken energy right here, and I turned it into force times distance. See this energy right here? It's work. This energy right here is work. I made it force times distance. Then I kind of separated it a bit, and I said, well, let's make that voltage is force over charge times distance. But we know that field strength is force over charge. That's another formula we have. So what I'm going to do is I'm going to take this little portion right here, and I'm going to substitute in electric field strength. Here is a new formula that we can use, which I believe this is one that is on your formula sheet, but it's written differently. Can you guys find the one on your formula sheet that goes like this? E equals voltage over distance. You guys see that one there? Here's the proof for how it was derived. They took three formulas and they shoved them all together and did a whole bunch of rearranging, and it created this formula here, which is essentially this guy here just rearranged. So another way to find your electric field strength is to take your voltage and then divide by the distance between the plates. Okay. A little while ago, I was talking to you guys about how voltage, a lot of kids, they think that voltage would be dependent on how far apart the plates are. That's not true. But your field strength is dependent on how far apart the plates are. Okay? So, you know how gravity, again, if I use my pen here, the distance the thing has to fall, that affects the gravitational energy, right? Well, it's not the same thing with your battery. The distance between the plates does not affect how much voltage the thing has, but it does affect how much field strength they have. So the long and short of it is if you put the plates closer together, you have a stronger field strength. If you put them further apart, you have a weaker field. Does that make sense? So if you have two really tightly close together plates, there's a lot of electric field between there. You separate them further apart, there's less field. So the other thing I need you guys to know here is that there's actually a third unit you can have for volts. Volts then can be your electric field strength, which is a Newton per Coulomb times by a meter. So that's actually another way of writing out its unit. You can do joules per Coulomb, or you can do newtons per Coulomb times by meters. Or you can do volts. All of the same. So here's that formula. Let's give it a try. You've got two plates. They are 16 millimeters apart. We know the field that we want to be is 800 newtons per Coulomb. Let's figure out the voltage. So this one's pretty straightforward. I just gave you the formula. The electric field strength for some plates is the change in voltage over the change in distance it has to undergo. So this number right here is your 800 newtons per Coulomb. Honestly, one of your biggest challenges is just knowing which numbers go where. You have to recognize that this right here, that is a field strength, so it has to go in the field strength location. What we don't know is the voltage, but I do know that they're 16 millimeters apart. I should just plug in 16 though, right? I need to put it into meters. So 0.016 meters. All I gotta do is just times that up there then. 800 times by 0.016 gives me a voltage of 12.8 volts. So what does that mean? It means that if you want to have this amount of strength between the plates in your battery, you better apply a voltage of basically a 12 volt battery. So far so good. Now it's pretty straightforward. It's just plugging into a formula. Well, the next question says, how much work is going to be done if an alpha particle moves from the positive to negative plate? It's at this point here that kids start to get a little lost where they're going, oh my goodness, there's formulas everywhere here. You have to kind of like figure out what you have and what would be useful. Because there's, what do we got, like 5 formulas in there that we've learned so far? Is any of those a formula for work? None of those formulas that are listed down in the electricity magnetism section have a W in it. That being said, what is work equivalent to? And we do have formulas involving energy, right? Probably the best one to use would be that the amount of voltage you have is going to be, the definition of voltage is how much energy happens per unit of charge. Well, we now know the voltage, right? Isn't the voltage 12.8 volts? If we want to figure out how much work is done, that's how much change in energy there's going to be. So I'll just put a W there. You need to know how much charge there is. Now this is the charge of the particle being moved. which I said was an alpha particle. So an alpha particle is 2 elementary electron charges of those. So I got this 4.096 times 10 to the minus 18. You guys get that value? What unit would that be? Oh, I did this wrong again. That's not a joule right there. This is one of the biggest struggles that you'll probably have too. You have to get your units right. This was charge. Charge isn't measured in joules, it's measured in coulombs. Okay, this work value right here then would be measured in joules, which I didn't tell you which unit to put it in, but if you didn't want to measure that in joules, you should be able to convert it to electron volts. All that means you got to do is just divide by 1.6 times 10 to the minus 19, and then you could get, like, say, 25.6 electron volts. You guys handle that calculation I just pulled off there? I think it's harder because it's more abstract. I'm not nearly as familiar with electron volts, coulombs, volts, as I am with meters, seconds, those sorts of things. So I have a hard time envisioning what a electron volt is, or what a coulomb is, or what a volt is, you know what I mean? Just because they're not things that we work with in everyday life. So you just have to wrap your head around what all these things mean again. So a coulomb is basically a lot of electrons. Okay. E, an elementary charge, is basically, well, how many coulombs we assign to one electron, which is a very small amount. A volt is how much energy you need per charge to move an item. That's your voltage. Energy per coulomb. Okay. We also call that a watt. No, not a watt. We call that a volt. Watts are later. You guys with me so far? There's a lot to jump into on day one here. Okay, last thing here. Would you be increasing your kinetic or potential energy if you did this? So let's draw this out here. You've got a couple of plates, and you're moving it from the positive plate to the negative plate. You're taking your alpha particle, which is positively charged, and you're moving it that way there. Is that the way it would naturally go? Actually, it is, isn't it? Wouldn't it naturally want to do that? So is that going to increase its kinetic or potential energy? Kinetic. Does that make sense? This thing is going to speed up. You guys ever heard of particle accelerators? Like there's a big one in Switzerland called the CERN Super Collider particle accelerator, where they smash small particles into each other. This is kind of the basic concept here. If you want to speed an electron up and shoot it, here's what you do. You put the particle on one side right here, and it's going to speed up as it moves towards the other plate. Only what you end up doing here, you put a hole in the plate so that it like literally shoots through like a gun. You'll see a lot of diploma questions where they show you diagrams like this, where you're seeing particles being moved between charged plates. All right, another example here. You got that alpha particle. We've got two plates. We've got the distance. We give you a voltage. Let's figure out how much force there is. So it's kind of like a puzzle. You have to use all these formulas and figure out how to get to what you're looking for. There's a couple of formulas involving force. One of them is this one. Fe equals kq1 q2 over r squared. That is a formula involving force. We're not using that one. Why? Why is that one not useful in this scenario? Yeah, that's the formula for the force between two just randomly charged particles nearby each other. That's not what we have. So the other formula we're going to need is F equals, well, it's rearranged. It's actually E equals Fe over Q. Hopefully you can kind of see how this is kind of a little bit of a puzzle. We have to kind of work backwards here. We need to know E and Q. Well, it's an alpha particle, so I know Q, but I need to find my electric field strength. I wasn't given an electric field strength, so let's use another formula that can get us electric field strength.
Please come to the office for checkout.
And so another one of those formulas would be electric field strength is equal to your voltage over your distance. And I do have my voltage and my distance. You gotta kind of see how this is gonna get pieced together. You're gonna take one formula and kind of shove it inside the other one. So there's two main ways kids will do this. The first way is they'll put numbers in for this to get here. Then they'll plug that into here for there. I'm going to recommend, let's try doing it algebraically. If E is equal to FE over Q, but E is also equal to V over D, can I write myself a new formula that says change in V over change in D is equal to FE over Q? You guys figure out how I kind of put that together? E is FE over Q, but I don't know E. E is also V over D. I do know V over D, so essentially these guys are equal to each other. I've made myself a brand new formula. Now let's plug some values in. This is 130 volts over 0.027 meters. I don't know my amount of electrical force because that's what I'm looking for. But I do know the charge because the charge is again an alpha particle. So it's 1.6 times 10 to the minus 19 coulombs. Let us solve that. I got 1.5 to the negative 15. Did I get that too? Boy, this is where you just have to know how your units work. The standard unit for volt is going to be the volt. The standard unit for distance was the meter. This one was at coulombs the way it's supposed to be. So by the time you're done, this should be newtons if everything works out properly. And we can prove it if we need to. What we really did is we took a volt, we divided by a meter, and we times it by a coulomb. You just need to go back through and memorize what all these things are equivalent to. A volt was actually a joule over a coulomb. Remember how a volt is a joule over a coulomb? Which then means that this coulomb right here and this over coulombs would then cancel. So you'd be left with, like, say, a joule over a meter. But isn't a joule a measure of energy, which is a measure of work? And a joule is then equivalent to a Newton meter. Which then means the meters cancels, which did, in fact, leave us with newtons. I don't need you to do all of this unit sort of work every single time. You just need to know what the standard units are and you'll be fine. But you should know all the equivalencies. Sound good? Cool. All right, I got one last example. Last example here. This is really like the creme de la creme, the biggest king of the mountain kind of question here, where this is going to take us possibly multiple different steps in order to solve here. Let's lay out the scenario here first. Part A, we're going to try to calculate velocity using kinematics and dynamics, and then later we're going to use energy. I'm going to show you two different ways of solving a fairly big problem where we're going to take one formula, go to the next, go to the next, go to the next. So here's the scenario. You've got an electron accelerated from rest between two parallel plates. So let's just arbitrarily assign this one to be positive and arbitrarily assign this one to be negative. I don't care which one's which, we're just choosing one. All right, let's put the electron on the negative plate. Why? Is it odd? Yeah, it'll repel and go towards the positive plate. Okay. My question for you then is, how much velocity in meters per second will this electron hit the other plate with? Right? Think particle accelerator. How fast is this electron going to hit the other plate here? Big V, voltage. Little v, velocity. We need more letters in the alphabet, right? So you gotta make sure you're very clear about the letters you're using here, because we're gonna have multiple E's and multiple V's, as well as all the other letters we deal with here. So let's see what we've got here. We've got a voltage between the plates, and we've got a distance between the plates. So based on what we have right here, I could then say that my electric field strength is equal to my change in voltage over my change in distance. Well, I have that, don't I? My voltage is 20 volts. My distance, if I convert it properly, is 0.04 meters. So I should be able to find my field strength. 500 volts per meter. Okay, well, let's see where that can take us. What formula now would be useful that also has an electric field strength in it? So as I look through the formulas, there's E equals KQ over R squared. That involves electric field strength. That one's not so useful yet. There's also one below it where it's E equals FE over Q. Let's use that one next. So then E equals FE over Q. Now I know my field strength. Now 1 unit for field strength will be volts per meters. But there is another alternative way of writing the units. Rather than volts per meters, it can also be written as newtons per coulomb. Because I actually know the charge. What object was being accelerated? And what's its charge? That number. Only I'm not timesing it by 2 this time because it's just got 1 electron, not 2. Right? Like an electron is 1 negative, not 2 positive. So if I times this up, hopefully you guys can calculate a force value. So 500 times by 1.6 times 10 to the power of minus 19 gives me a force of 8 times 10 to the minus 17. That would be in newtons. We've got a force value. What's Newton's second law? Force is equal to mass times acceleration. Well, I know its force value. 8 times 10 to the minus 17 is its force. But you know what? If you go to your formula sheet, you should be able to find the mass of an electron. Flip to the back side of your formula sheet where all those numbers are. You guys find the section where it talks about particles. You guys see the mass of the electron there? It's 9.11 times 10 to the minus 31 kilograms. So based on this, I should be able to find myself now an acceleration. This should tell me how fast my electron is accelerating as it hops from the negative plate over to the positive plate. It's accelerating at a rate of 8.78, etc., times 10 to the 13 meters per second squared. Oh, we've already done like 3 formulas here. I think in this example here, it makes more sense just to find numbers one as you go along, and just like go this one to this one to this one. We're almost there. I have an acceleration. I know how fast this electron is accelerating. But really what I'm looking for is I'm looking for its velocity final. What is its velocity initial? Accelerated from rest. I have the acceleration. I also know how far it's traveling because it's traveling 4 centimeters. Yeah, see how the last step here is going to be to use a kinematics equation? So that formula is velocity final squared equals velocity initial squared plus 2AD. Velocity initial, 0. Your acceleration we just found, I'm just going to draw an arrow. And your distance is 0.04 meters. Don't forget to square root by the time you're done too. Eh? Velocity final, 2.65 times 10 to the 6. You guys get that? Okay, I went fairly quick through that question for two reasons. One, I'm running out of time. But two, I do want to stress you a little bit here. Because this is the sort of thing that, I mean, need you guys start being able to work on is, we used 4 formulas, I think. Right? And this was like a long puzzle where you like used Formula 1 to get this, and then Formula 2 to get this, and then Formula 3 to get this, and then Formula 4 to finally get your answer. And this is really where the challenge of Physics 30 comes in, is hopefully you agree. Individually, all those formulas are pretty easy, I think, right? They're all like 2, maybe 3, maybe 4 variable formulas, not all that much, right? But it's now the train where A gets you B, B gets you C, C gets you D, D gets you E, you're finally done, right? That's the puzzle I need you to be able to solve, right? If you can follow that pattern, then that's the skill I need you to possess. Does that make sense? The reason why I think this is challenging is you have to know which formulas have similarities to other ones. So you have to know, okay, well, this is a force. There are other force formulas somewhere else on the formula sheet, right? This is an electric field. Don't get electric field mixed up, though, with energy, because they don't mesh. Sound good? Okay. Let's try one last example here, if I can, before the bell goes here. I want to do the exact same thing, only let's try using energy instead. This is going to be much faster. I promise you, this won't take nearly as long. Often there are multiple ways of solving questions depending on which loop you want to take. You can go A to B to C to D, or you can go A to X to Y to D. Like there's alternate routes. Consider this formula here. We could use the fact that voltage is equal to your change in energy over charge. That's a formula on your formula sheet. The voltage was 20 volts. I'm going to look for the change in energy. And the charge, well, it was an electron, right? So an electron has a charge of 1.6 times 10 to the minus 19 coulombs. So I should be able to get myself a change in energy by just multiplying those numbers, right? So I've got a change in energy of 3.2 times 10 to the minus 18 joules. What else is energy equivalent to? Well, what sort of energy is taking place here? We're changing potential into, and don't we know the formula for kinetic is 1/2 mv squared. Now, if it's starting at rest, won't the velocity we solve for here then be the final velocity we have? So then make that equal to 1/2. Well, we need the mass again, don't we? The mass was 9.11 times 10 to the minus, I used to have memorized 31. Yep. 31. And that's equal to this value right here. So times by 2, divide by the mass of the electron. Don't forget to square root it. Is that an answer? One of them was quicker, right? Often you'll have multiple paths to the same spot. You guys in my Chem 30 class last year, remember talking about Hess's law? The idea that you can kind of like combine chemical equations? It's kind of like that in a way, where there's probably a pathway 1 that goes this way, there's a pathway 2 that goes this way. One was probably shorter. I think you guys would agree with me that the second pathway was way faster, right? In terms of how many steps we had to do. It's your puzzle, though, to figure out as to which formulas kind of link to each other. Can I have one last thought? Using the second method, you guys see how we had 4 centimeters right here? Hypothetically, let's say that I didn't give you this distance right here. You'd be forced into taking this method right here, because see how this method here, we didn't use a distance? You know what I'm saying here? Right? Whereas right here, I did use the distance, like right here, and I did use distance again later. But it is possible that of the 2 choices, you might not actually even have a choice, depending on the information you're getting. Okay, sorry I ran out of time. We'll talk more tomorrow. Thanks for being patient for like, how long was this? An hour and 10 minutes.